polynomials that you already know can be represented in the form of beautiful diagrams. Let's look at a plus b square, for example, right? Rather than just remembering the expression a plus b the whole square is a square plus 2ab plus b square, you could visualize it, right? It's a plus b square, right? So I'll take a plus b and make it into a square, right? So this side is a plus b, this side is a plus b. Now draw this line here and this line here, right? This region, what you get is a squared. This region here is b squared. Both of these are ab. That's how you get a square plus 2ab plus b square, right? There, a very simple polynomial that you've already learned could be visualized, right? So all polynomials can be visualized this way. The entire chapter we are going to learn in this way through visualizations, right? So they need not be boring algebraic expression. They need not be boring variables. They can be extremely interesting figures with lots of bright colors like the ones we saw in the beginning, which are complex polynomials, or the simplest of ones can be expressed in the form of visualizations, right? What is math at the end of the day? Math is nothing but a language, right? Just as painting and art are forms of expressions or languages, so is math, right? And this language of math actually has several dialects, right? Diagrams and visualizations that we saw is one dialect. Variables could be another. Polynomials, you're used to writing them in variables, right? So variables is another dialect. Numbers is another dialect. Or they could be applications and words in which you describe a mathematical scenario, right? All of these are different dialects of the same language, and hence you can say anything in all of these four forms, right? So you're used to always thinking of polynomials as variables. They need not be. We just saw that they could be beautiful diagrams and graphs. They can also be numbers in a very similar fashion, right? Let's say we have a series of numbers 1, 2, 3 and 4. If I tell you, write these numbers using a variable, you can easily write that. You can say that all of these are nothing but x. These are nothing but x, where x is any natural number, right? That's how you represent this series. Instead, if I give you another series, 1, 4, 9, 16 and so on, how will you represent this? How will you represent these using a variable? What are these numbers? These are nothing but square numbers. So you'll write them as x square, where x is again any natural number. Correct? So just as we saw that polynomials can be represented as diagrams, they can also be represented as number patterns, right? Each polynomial at the end of the day represents some diagram, some number pattern, some application. It's just another way of expression, right? Similarly, if you have an application stated in words, right? Say the list of all odd numbers. List of all odd numbers. Can we write this using a variable? Using numbers, it's very easy, right? We know 1, 3, 5 and so on. Okay, list of all positive odd numbers, let's say. So 1, 3, 5, 7 and so on. Can we write this using a variable? Can we write this using a variable? Can you write this as 2x plus 1? 2x plus 1? What are odd numbers? Odd numbers are any multiple of 2 plus 1. That's an odd number, right? Even numbers are all multiples of 2. If you add 1 to it, you'll get an odd number. That's the logic that we used. If x is any whole number, 2x plus 1 will be the list of odd numbers. Correct? Because you're taking a multiple of 2. 2x is nothing but a multiple of 2 and you're adding 1 to it. If x is 0, you'll get 1. If x is 1, you'll get 3 and so on, right? For different values of x, you'll get the entire list. So all of these variable-based representations that we just did are nothing but polynomials, right? All of these are nothing but polynomials. So polynomials is in general the variable-based dialect in the language of math. That's all that polynomials is, right? It's a type of language. We are used to studying them in variables. They need not be, right? We just saw how polynomials can be diagrams, how they can be number patterns, right? That's how we'll be studying this entire topic. Take a polynomial, understand it in all of these forms. The moment you do that, it becomes very, very simple. So we understand so far that polynomials are some kind of a string of variables and numbers put together, right? So we understand that it's some variable-based representation. There are a lot of things put together and we called all of this stuff polynomials, right? But what exactly are polynomials? What exactly are polynomials, right? If we continue our analogy with a language or with English, let's take a polynomial and then break it down, right? Let's start with a polynomial. Assume that I'm speaking the truth to you and accept that the polynomial I'm giving you is actually a polynomial. Let's say we have 4x cubed minus 3x square plus x by 4 plus 6. Okay, this is the expression that we have. This is the expression that we have. It's an expression in variables. This is what we call a polynomial. Now, what are the conditions? Can we write anything and will it still be a polynomial or no? We'll come to, right? Let's go one by one. So you see some symbols here. You see some pluses and minuses here. Now, if you compare it to English, I'm going to compare this. I said that it's a language, right? At the end of the day, we are much more familiar with English as a language than polynomials as a language, right? We converse every day using English. We rarely converse using polynomials, right? You never say that, oh, my brother's age is 2x plus 5 where x is my age. Thank goodness we don't talk like that, right? So we don't, right? Hence, let's use something that we are more familiar with, which is English, and compare it, use an analogy to understand what this polynomial is all about, right? So you see pluses and minuses here. Pluses and minuses are equivalent to spaces in English, right? Are equivalent to spaces. So what do spaces do? If you think of pluses and minuses as space, in a sentence, if I write a sentence, my name is Anita, what does a space do? A space is separating two words, right? It's separating my and name, separating name and is separating is and Anita, correct? So every space is separating two words, which means that if I look at this polynomial, I have three spaces, 1, 2, and 3, right? So these should be 4 words, right? 1, 2, 3, and 4. My spaces should separate words. So these are 4 words. Now, instead of calling them words, because it's not English and it's polynomials, we have another term. So words are nothing but terms, right? So you know that words are separated by spaces. Now, instead of calling them words, when we look at polynomials, we call them as terms. So in this polynomial, you have 4 terms. You have 4 terms because you have 4 words, right? 3 spaces which separate 4 words. Very easy so far. Now, let's pick one of these terms, right? So let's keep the polynomial aside. Let's just take one term and see. So we understand that there are 4 terms now. Now, within a term, what all is there, right? We saw spaces and terms. Now, let's look within a term. So I have 4x cubed. This is the term. What do different parts of this term represent? This 4, you see a number, this is a variable, right? You see a number and a variable, right? You have 4, which is a number. You have x, which is a variable, right? So we call this a variable. The number that you have along with the variable, this is 4 multiplied by x, right? 4x is nothing but 4 multiplied by x. So the number which is multiplied with a variable, we call this as the coefficient. So the 4 in this case is the coefficient. So x is the variable, 4 is the coefficient. And this 3, x is raised to 3, right? That is the power or the exponent of x. So every term will have just these 3 things. It will have a coefficient, which is multiplied by a variable, and the variable will be raised to some exponent or power. That's it. In this case, we have just one variable. You might have a polynomial with many more variables, right? You could multiply this by y, z, any number of variables, does not matter. Right? So these are the 3 things that every term will have. So a polynomial will have some spaces. Those spaces will divide the polynomial up into terms. Each term will have these 3 things: a coefficient, variable, one or many variables, and each of the variables will have an exponent or a power. Now, let's see, are there any conditions on these? Can I have any coefficient? The answer is yes. You can have any coefficient, any real number could be a coefficient. No restrictions at all, right? So it need not be positive, for example. This is plus 4, right? It could have been minus 4. It need not be a whole number. It can be a fraction, right? It could be 3 by 4. Does not matter. No conditions at all. Any real number could be your coefficient. Very good, right? Variable anyway varies, right? So it cannot have a condition. There is no limit on the number of variables either, right? If there's only one variable, you'll call it a polynomial in one variable. If there are 2 variables, you'll call it a polynomial in 2 variables, and so on. But essentially, no condition on the number of variables. So coefficient can be any real number. You can have any number of variables. No conditions so far. Now, the remaining thing we have left is the power or the exponent. Here, we do have a condition. This power or the exponent has to be a whole number. It has to be a whole number. So you can have x cube, you can have x square, but you cannot have root x, for example. Why can you not have root x? How can I write root x in terms of a power? Root x, I can write it as x raised to 1 by 2. Now look at my power, it's 1 by 2. Is 1 by 2 a whole number? It's not, right? So this cannot be. This cannot be a polynomial. right? That's the only condition. The power or the exponent has to be a whole number. Has to be a whole number. No condition on variables, no condition on the coefficient. The only condition is on your exponent or power, which has to necessarily be a whole number. That's it. You know all about polynomials. It's done. That's all that there is to it. You know terms, you know how many terms a polynomial has, you know what different things in each term mean. That's really all there is to polynomials, right? Now, just as you're comfortable with the language of English, you're comfortable with the language of polynomials once you know these words. Now, notice that the condition I gave you for the power or the exponent was that it has to be a whole number. I said it has to be a whole number, not natural number, which means that it can be 0. It can be 0. What happens if I have x raised to 0? In the same term, instead of having it as 4x cubed, what if I had it as 4x raised to 0? What is x raised to 0? X raised to 0 is 1. Any number raised to 0 is 1, right? Doesn't matter whether it's a variable or constant. Any number raised to 0 gives us 1, which means 4 into x raised to 0 is going to give us 4. And this is a valid polynomial because our condition on the exponent was that it has to be a whole number, which means it can definitely be 0. So 4 is a very valid polynomial. Such a polynomial, we call it as a constant polynomial because there's no variable, right? Technically, yes, there is x raised to 0, but the value of x raised to 0 is 1. So essentially, there is no variable. It's just a constant, right? It's just a constant. 4 will always remain 4, right? It does not vary. No matter what happens, 4 will always remain 4, which is why it's called a constant. Such a polynomial, we call it as a constant polynomial. Now, if we go back to our original term, so we understand the constant polynomial. If we go back to our original term, 4x cubed, now the coefficient didn't have any conditions, right? Coefficient could be any real number, we said, which means that instead of a 4, I can have a 0. So let me take out the 4 and put a 0. I can have a polynomial like this, very valid, right? Because we didn't say that the coefficient cannot be 0. So I can have a polynomial which is 0x cubed. Now 0 multiplied by anything is going to give you 0, right? So the value of this polynomial is going to be 0. This is also a constant polynomial. Such a polynomial, we call it as a 0 polynomial. And you'll see why we have in the next 10 or 15 minutes, you'll find out that why 0 has a special significance, right? Why can I call 1, 2, 3, 4 just constant polynomials and 0 I give a special name as 0 polynomial? We'll see that in a few minutes. So when it is 0, we call it a 0 polynomial, right? That's all there is to polynomials. We understand all the terminology now, right? So if we go back to the other terms of our polynomial, we looked at the first term, which was 4x cubed. Let's pick the second term, minus 3x squared. What is the coefficient here? Coefficient here is minus 3, right? Don't pick just the number. Pick the number along with the sign, right? Because 3 and minus 3 are different numbers, right? So minus 3 is the coefficient. Minus 3 is the coefficient. X is nothing but the variable. 2 is nothing but the power or the exponent of x, right? Similarly, if you pick the next term, it's plus x by 4, right? X by 4 means I can write this as plus 1 by 4 into x. So 1 by 4 is my coefficient, x is my variable, x meaning x raised to 1, right? So 1 is the power or the exponent. The final term, if you pick plus 6, this is a constant term, right? It doesn't have a variable, which means the variable is raised to 0. 6 is the coefficient, right? So that's the terminology for describing every part of any polynomial, right? There's just one more term we need to know, which is now we know the exponents of each of these individual terms. What if you look at all of these terms together? If you look at all of these terms together and pick out the highest exponent, this one had exponent 3, this one had 2, 1 and 0, right? Let me pick out the highest of these, that will be 3, right? So I pick the highest exponent and I give it a name. This is called the degree of the polynomial. The reason we pick the highest power and the reason it's significant is because that determines largely how the shape of your polynomial is going to look. So this is called the degree. Just look at all the powers or exponents and pick the highest one. That's it. That's what the degree is, right? So in this case, the degree of this polynomial is 3. Now, these polynomials, right? Polynomials means something having many terms. Poly is many, right? Polygon, right? Polygon is a shape having several sides. Now, depending on the number of sides, you give polygon specific name. If a polygon has 3 sides, you call it a triangle, 4 sides, quadrilateral, 5 sides, pentagon, and so on, right? Depending on the number of sides. Similarly, depending on the number of terms, we can give different types of polynomial special names. So if it has only one term, this one had 4 terms, right? This polynomial had 4 terms. If it had only one term, let's say, I would call it a one-term monomial, right? Monomial, 2 terms, binomial, 3 terms, trinomial. Very easy, right? Okay, so depending on number of terms, you have these names, right? Monomial, binomial, trinomial, and so on. Now, depending on the degree, again, you can have a set of names. If you look at the whole expression, there are 2 things, right? How many terms are there and what is the degree? That's where we look at the whole expression, right? So based on both of these, there are names. So based on number of terms, we know monomial, binomial, trinomial, right? Now, based on degree, if the degree is 1, you call it a linear polynomial.